Alright guys, so welcome to 6.1 Discrete Random Variables. So today we're going to talk about a discrete random variable that takes a fixed set of possible values with gaps in between values. So discrete meaning that it is a fixed set of possible values with gaps in between, alright? And then we're going to also talk about continuous, right? So continuous can take on any value in intervals. So continuous could be things like time, your height, your weight, things like that are continuous, right? You weren't born and automatically weighed 170 pounds or whatever you weigh, right? You actually grew up to that point, okay? Same thing with height. You grew up, you started small and you grew. It wasn't like you were at 1 foot tall and then you automatically were 6 feet tall the next day. So with that, it's continuous, okay? A discrete random variable will be things like how many cars you own, how many computers you own, things like that, right? You'll have 1 car, you'll have 2 computers, you'll have 3 basketballs, 4 footballs, however the case is, right? A discrete random variable, okay? So we'll talk about those 2 things today, as well as histograms. And the big thing is describing the shape of those histograms after we make them. I know this kind of goes back into beginning of school when we talked about dealing with histograms and different types of charts. But with this one, on the histogram, our probability is going to be our y-axis, and our value is going to be on our x-axis. And the big thing with that is after we're able to make a histogram out of these with discrete random variables, then we're also going to want to be able to describe the shape. And another big thing, calculation-wise, we're going to talk about is the mean for the expected value. And so with that, as you can see right over here, we've got our big E, or our sigma, right? Which this means the sum of, with most of you probably already understand that. So we're talking about the sum of all of your x values. So x with your subscript I is your initial x value times the probability for that initial value. So every x value times this probability. And we're adding those all up, and that'll give us the mean value for that, okay? So that's what we're going to talk about today. We'll go through a little exercise here I like to work with on these problems, all right? So I like to do this as far as saying x is the number of children somebody has in their family, okay? So suppose we choose someone in the class at random. And this data here is from previous class I've dealt with when I had 26 students. And of course, just with these, it went on as far as 1, 2, 3, 4, 5, and 6, or 6 plus, I should say. And what that included was themselves is in that count, as well as any brothers or sisters, and whether that be, adopted, blood, whatever the case may be. Okay, step, whatever the case. So with this, you see the values there, going through those probabilities with that. So the next thing I really want to talk about, the first thing you should really think about is, does this probability make sense? Is it valid? And how do we verify that? Well, hopefully you remember that all the probabilities should add up to the value of 1. In which case, we can look at this and see what we got here, right? So we've got 26 down at the bottom for our denominator. Let's see if our numerator adds up. So in which case, we had 2 over 26, 6 over 26, 7, 5. Alright, so that gives us, see, we got 2, 8, and 7 gives us 15, and 20, and then 26. So we got 26 over 26. So this should give us 1. So we know we're good with that. And well, what's the other thing? We also got to make sure all the probabilities are between 0 and 1 to begin with as well, right? So with that, we can see that all these are a fraction of 26, so they don't always go above 1. So with that, we're also good between 0 and 1. So we're also between 0 and 1. So we're good there. Okay, so also now we said this is the number of children, right? So x, as far as being 1, 2, 3, and so forth, okay? So if I had, let's think about this, if I had, let's say, could I use the value of x equals 5.0 7167. Could I use it as an x value as far as saying the number of children is 5.7167? No, we can't do that, right? You can't have part of a child. We cannot have 0.67. You can't do that. So with that, no. So again, no, cannot have a part of a child, right? So that's telling us that this is discrete. Okay, it's discrete. We're not looking at continuous here. We're looking at a discrete variable, okay? So next thing let's talk about is let's go ahead and see if we can do a histogram with this. Let's see what we'd have to do to make a histogram for this. Alright, so with the histogram, again, our y-axis is going to be dealing with our probability, and our x-axis is going to be dealing with our values. So let's go ahead and just make our little bar here. And we've got for x values, so label it x values, because we know that's for our number of children, right? Use label number of children. I'm saying x value so you can follow along with me. So 1, 2, 3, 4, 5, and 6. Okay. And then so for our probabilities, out of these, let's go ahead and make this kind of easy here. So we have up to 6 plus, right? So we're gonna say we go up to 6 then for our values or probabilities, because the highest, oh I'm sorry, 7. The highest probability I had was 7 out of 26 for the for 3 children. So we'll label that 1, 2. So we're going to say the probability on the other side, and that is, we're going to label that just 1 through 7. So we can say this is n 1 over 26. Okay? Now my handwriting looks really bad, but we'll say 1 and 26. Try and write that 6 a little bit better. So 1 and 26. So that's what we're talking about here. You put in there for your probability. The reason why we can just go from 1 to 7 here to make this a little bit easier to write out. So now we're just having to graph these out. And again, the histogram is different from our bar graph because we're looking at the bars should actually connect, right? And the histogram is dealing with a group, right? So we're looking at this going for the 1, we went up to 2. So up to 2 here. And then for the 2 we had 6 students that had 2. Another thing is make sure you keep the bars all as equal distance as you can. I understand, like myself, it's not easiest thing in my scribble scratch, but definitely make sure to make them look as close to being the same width as you can, because you don't want to have it too out of the norm to where it makes the grader think about it. Okay, so then we got 4 for the 5 children. Oh my goodness, that was scary. Erase that one a little bit. 4, and then we had 2 again. Okay. So with this now, like I had mentioned, now we want to talk about with this is we have our axes labeled and we've connected all our bars here. We've got all the probabilities going. So now we want to describe the shape, right? So we want to make sure we describe the shape. And with this, hopefully you guys can see this kind of looks like your right foot there, okay? Because like your big toe over here, then go down to your pinky toe, it's slightly skewed, right? It's not 100% just blown out skewed, but we'll say slightly skewed right. So slightly skewed right. And we can also say with a single peak, okay? The single peak at the value of 3, because 3 we had our highest at 7/26, okay? Slightly skewed right with a peak, say a single peak. So I would leave out that, all right? So they understand with the peak, single peak at 3, okay? So describing it again, talking about the shape. And in this case, we want, so it's easy to describe the peak and where it kind of lands. In this case, the 3s, we want to go ahead and include that in the description as well. All right. So now let's look at it a little bit of probability-wise. We're talking about with these guys. So let's see, describe in words, and then we'll also find the probability of our x of being greater than or equal to 3. So the probability of x being greater than or equal to 3. So we're going to be looking at those guys. We're looking at these values right here for our probability, right? So with that one, the probability that it has at least 3 and more, right? So to describe that, that's what we'd be saying. So again, we would be saying, to describe that, we would be saying the probability that a randomly selected student has 3 or more children in their family. And then let's find out what that probability actually is. Again, we're simply taking those values. We're taking 7/26 plus 5/26 plus 4/26 and then plus 2/26. And so that would give us 12, 16, 18/26. And let's get that calculation going real quick. And that should give you 0.6923 for our probability for that. Okay. So with that, let's see, what would be the difference then if we were to say we just wanted to have the probability of x greater than 3. Right? The only difference there is we're not actually including the 3 anymore. Then we're just including 4, the 6 plus. So in that case, we would want to say the probability that a randomly selected student has 4 or more children in the family. Or you can simply say greater than 3 children in their family, okay, for describing that. So with that, we would simply be taking the probabilities again. We would be adding those up. We would not include the 3, so the 7/26. We're left with 5 plus 4 plus 2 all over 26, which would give us 11/26. And that would give us 0.4231. Okay, so those are our 2 probabilities for those types of questions asked, especially when you're given the values like that. All right. Okay, so now let's find the average of the x values we have here. So we can see the average of children we got here, right? So to do that, we would simply be taking 1 plus 2 plus 3. Well, if I write a 3 here, plus 4 plus 5 plus 6. And we'd be dividing that by, well, the value that we have there, right? We have 6 numbers altogether. and that should give us 3.5, right? So is that telling us that the average number of children in families for students in this class is 3.5? What do you think? Well, I don't really feel that was saying that everybody in the class has the average number of siblings is 3.5, or children all in general, right? For family, that doesn't sounds pretty big, right? Everybody's got a big family if you got that. So I'm going to say no, right? The number 3 will have a large impact on the mean, since there is 7 to the 26 in there, right? But let's look and see how we need to really do this to find the actual probability, or the average number of children, I should say, in the class. So let's look at this real quick. We would simply be using that equation we talked about earlier, where we take our sigma, right, over x initial times our probability of initial. So for these, we would be taking 1 times 2 over 26, and so forth, okay? Alright, so once you've written that all out, then you can see that the actual probability is going to weigh a little bit different on those values instead of just giving us 3.5. So let's put this in our calculator and see what it gives us. Alright, so after putting it in my calculator, I came out with 3.3462. Alright, so again, those values there were weighed heavily with dealing with our value here for our 3s, right? And our 2s even a little bit, maybe. That's what probably dropped it down a little bit as far as going off 3.5, just the overall mean of it, if we just add all the x values up and then divide by 6. Well, because we still had a decent amount of 2s and a little bit of 1s there, that pulled it down away from the 3.5, which is going right here in between our 3 and 4s, because we had 7 and 5 there. So it pulled that mean down a little bit, which hopefully makes sense, right? So probability of weights is what pulls it in the direction it needs to go. If we would have had that 6 up here at our 5s and had a 4 down here at our 2s and whatnot, it probably would have been a lot closer to 3.5, if not a little above it. In which case you can play around with that and see how that works out. But again, so with that, that's the equation you're looking at as far as dealing with your mean overall, right, for probabilities. The sigma, your sum of the x values times each probability for that x value. So with a discrete random variable, it takes a fixed set of possible values with gaps in between the values. So again, dealing with, like we talked about with cars, or how many computers you own, how many basketballs or footballs you own, things like that, right? Discrete random variable. Continuous is dealing with like your height, your weight, okay? Continuous, right? Time is continuous. And the histograms, don't forget, and the bars are all touching as we show there, as well as label your actual probability and x values. So label your x and your y value, x and y axis. And then for sure, this is the key equation to take away from this on the big ideas. As far as dealing with your mean for the expected value, is your sigma, in other words, the sum of all your x values times those probabilities. Alright guys, so we learned a little something today, and I'll see you next time.